video, we're going to discuss work. So before we discuss work, we have to talk about force. A force is a push or a pull on an object. And we have the equation that force equals mass times acceleration. And as calculus students, we know that we can express acceleration as the second derivative of the position function of some object with respect to time. So this is acceleration, and this is the mass of the object. Now, when we're measuring force, if we're working with SI metric system, we measure force in newtons, and a newton is a kilogram meters per second squared. And you can see that makes sense by the definition of force. Mass is measured in kilograms, and then acceleration is going to be in meters per second squared. If you're working with the US customary system, force is measured in pounds, which we abbreviate LB. Now, when acceleration is constant, that means force is also constant, right? Because all you're doing is multiplying mass times acceleration. So if this quantity is constant and mass isn't changing, right? Your object's not decomposing as time goes by, then force is going to be constant. And then we can compute work as force times distance. Now, what are the units or the measurement applied for work? Well, the SI metric system uses a joule, J. And the US customary system is a foot-pound. There's no cleaner way to write it. You could just write FT-LB if you want to abbreviate, but we say foot-pound. Okay, so let's look at some examples here. And you need to be familiar with both measurement systems. So how much work is done lifting a 1.2 kilogram book off the floor to put on a desk that is 0.7 meters high? Use G equals 9.8 meters per second squared for acceleration. So that's the force of gravity, right, on the earth. So a 1.2 kilogram book, that represents the mass of the object. And then this is the distance. So I'm going to use that to compute work. But first things first, I need to get force. So force, we know, is mass times acceleration. And in this case, we're going to use 9.8 meters per second squared. So I have 1.2 kilograms times 9.8 meters per second squared, and we get 11.76 newtons. Now, typically in math, we don't use sig figs, significant figures, so just check with your instructor or follow the directions regarding how many decimal places they would like you to use for your answers. And then for work now, I'm going to take force and multiply by the distance. And in this case, the force is 11.76 newtons. The distance is 0.7 meters. And we got 8.232 joules. And that's our final answer. All right, moving on. How much work is done in lifting a 20-pound weight 6 feet off the ground? So here we're given the weight of the object, which is actually already its force. So note, or the force being applied to it. So weight is a force. You don't need to multiply by G. And that's sometimes confusing because people speak incorrectly, especially in this country. It's common to hear people say, oh, I really want to lose weight. Well, in order to lose weight, all you would need to do is go to the moon, right? The gravitational force there is less than it is on the earth. But what they really mean to say is, I want to lose mass. So anyways, we already have a force, which means if I can just go ahead and compute work right away. So the work is going to be 20 pounds. Times 6 feet that we need to lift it off the ground. So this is going to be 120 foot-pounds. All right, now let's take the situation and suppose that our force is not constant. Say it's variable. In that case, we would integrate from A to B, f of x, which is our force function, dx. What do A and B represent? Basically, your object is moved from A to B. Okay, so let's look at an example here with a variable force function. So example 3, when a particle is located x feet from the origin, a force of x squared plus 3x pounds acts on it. How much work is done in moving it from x equals 2 to x equals 5? So let's set up our integral. This problem's pretty straightforward. So the work is going to equal the definite integral from 2 to 5 of x squared plus 3x dx. And this is going to give us 1/3 x cubed plus 3/2 x squared evaluated from 2 to 5. All right, now let's plug in our upper and lower limits. So 5 cubed, that's going to be 125 over 3, plus 5 squared times 3, that's 75 over 2, minus 2 cubed, that's 8 over 3, plus 2 squared, that's 4, but the 4 and the 2 are going to cancel, so I'm left with 6. And then, getting a common denominator, we get 423 over 6, which you can reduce to 141 over 2 foot-pounds. Don't forget your units. Okay, nicely done. Now let's look at another application here, and it has to do with Hooke's law. Hooke's law tells us that the force required to maintain a spring stretched x units beyond its natural length is proportional to x. So f of x is equal to kx. So k is the spring constant, and it's going to be unique to each individual spring, depending on the material that it's made of, as well as the thickness of the coils. So the idea is, say you have some spring, and maybe this is its natural length, okay? Hooke's law tells us that the amount of force required to stretch it beyond this point, but beyond where it naturally, its natural length, is proportional to how far you're stretching it. Okay, so let's see what sort of applications we can solve with this problem. So a force of 30 newtons is required to hold a spring stretched from its natural length, 10 centimeters to 16 centimeters. How much work is done in stretching it from 16 centimeters to 19 centimeters? Okay, well notice they give us two sets of information. The first part of the problem tells me a force of 30 newtons is required to stretch it from 10 centimeters to 16 centimeters. The purpose of this info here is so that we can find K. Once I found K, then I can focus on the second part of the problem, which asks how much work is done in stretching it from 16 to 19 centimeters. So once I get K from the first bit of info, then I'm going to go ahead and figure out how much work is required. Okay, now make sure that we convert to meters, right? We have to have everything in our standard units for the metric system, and everything's given to me in centimeters. So we're just going to divide everything by 100. All right, so f of x, I'm going to use Hooke's law. F of x is equal to kx. So first I'm going to find k. And so they told me a force of 30 newtons is required. I don't know what K is, and I have to stretch it from its natural length of 10 centimeters to 16 centimeters. So how much beyond its natural length is it getting stretched? Well, I take 0.16, right? That's 16 centimeters converted to meters, and I subtract the natural length. Or you could just know, hey, that's 0.06 beyond its natural length, 0.06 meters times K equals 30, which means K is equal to 500 for this particular spring. So now I know my force function is 500x. Okay, now we can move on to the second part of the problem, which asks how much work is done in stretching it from 16 centimeters to 19 centimeters. So the spring is moved from 16 centimeters, so the lower limit of integration is going to be 0.16 minus 0.10. I have to subtract off its natural length. No work is being done to maintain the spring at 10 centimeters. That's its natural length. No force is being applied. It's only beyond that. So subtract off the natural length. And then the upper limit similarly would be 0.19 minus 0.10. My force function is 500 x dx. Okay, and then this integral is not too crazy, so we're going to have 500 x squared over 2 evaluated from 0.09 to 0.06, which is going to give us 250 times 0.09 squared minus 0.06 squared, which is 250 times 0.0081 minus 0.0036. So we have 250 times 0.0045, which is 1.125 joules. All right, very nice. Next example, a little different scenario. A chain lying on the ground is 10 meters long and its mass is 80 kilograms. How much work is required to raise one end of the chain to a height of 6 meters? Well, first thing, I want to figure out what the mass is per unit. Since the entire chain is 80 kilograms and it's 10 meters long, then that means the mass per unit is 8 kilograms per meter. Now the force required to lift it is going to depend on overcoming the force of gravity. And the work is going to be applied from 0 to 6, since I have to raise one end 6 meters. So the work is going to be the integral from 0 to 6. I have 8 kilograms per meter, so 8 times 9.8 times x, representing each unit of the chain that's getting lifted, dx. And this is going to be 39.2 x squared, evaluated from 0 to 6, which is 39.2 times 36, so 1411.2 joules. Okay. Good. Now let's look at another spring application, a little more complicated. So if 6 joules of work is needed to stretch a spring from 10 centimeters to 12 centimeters, and then another 10 joules is needed to stretch it from 12 centimeters to 14 centimeters, what is the natural length of the spring? Okay, so to begin, we're going to let A equal the natural length of the spring. And they've given me 2 different sets of information. They've told me 6 joules is needed to stretch it from 10 to 12 centimeters. So as an integral, that means 6 is equal to, because that's the work, the integral from 10 to 12, that would be 0.10 minus whatever the natural length is, and then 0.12 minus whatever the natural length is. I also don't have k, kx dx. So that's from that first piece of info. Also, they told me that 10 joules is needed to stretch it from 12 to 14 centimeters. So I could set up another integral. I have 10 is equal to the integral from 0.12 minus a, because we're stretching it from 12 to 0.14 minus a, switching everything to meters, remember, kx dx. So notice here, I have 2 integrals. I have 2 unknowns in each of these integrals, right? I don't know what a is, and I don't know what k is. Well, we've been in this situation before, probably as algebra students, but still, we have 2 equations, 2 unknowns. We can solve this system. Okay, so we're going to evaluate each integral, and then we'll end up with the result with k's and a's in it, and then we'll have two of those equations, and then we'll solve the system from there. So working with the first one here, we have 6 is equal to, so antiderivative of kx, that's going to be kx squared over 2, evaluated from 0.10 minus a to 0.12 minus a. And then 6 is equal to k over 2. And then I'm going to have 0.12 minus a squared, plugging that in for x, minus 0.10 minus a squared. Okay, now I have to multiply everything out. And while I'm at it, let me just multiply this 2 over to the other side. So I have 12 equals k times 0.0144 minus 0.24a plus a squared minus 0.01 plus 0.2a minus a squared. And this is nice because notice the a squareds cancel. So this won't be too crazy of a system to solve, we can see now. And then I can combine my like terms, so I have 12 equals k times, I can combine these guys here. So I have 0.0044 minus 0.04a. I'm just going to leave it like that for now, okay? So put this on the back burner, and then now we're going to evaluate the other integral that we have. So the other one, where are you? This one. Super similar process, right? So now we have 10 equals kx squared over 2. This one's going to be evaluated from 0.12 minus a to 0.14 minus a. And then really similar process as last time. I have 20 equals k times 0.14 minus a squared minus 0.12 minus a squared. And then you multiply it out, combine your like terms, and you should end up with 20 equals k times 0.0052 minus 0.04a. So here's our second equation. Okay, so now here's our system. We have this first equation and this second equation, so I'm going to stack them now and solve this system. So we have 12 equals k times 0.0044 minus 0.04a. And I have 20 equals k times 0.0052 minus 0.04a. Okay, lots of different ways to solve the system, especially it's linear. Oh no, it's not, because if you distribute the k, you have ka. Anyways, I think the best thing is we can divide the equations by each other and cancel the k out. The only thing is I'd rather have the second equation on top instead, and we know k is not going to be 0, so we're allowed to do something like this. So let's rewrite these guys down below as 20 equals k times 0.0052 minus 0.04a, and then I'm going to divide it by the second equation, 12 divided by k times 0.0044 minus 0.04a. So then now k cancels out. 20 over 12, that's 5 over 3. And then I have 0.0052 minus 0.04a in the numerator over 0.0044 minus 0.04a in the denominator. And then you can cross multiply. So we have 0.022 minus 0.2a equals 0.0156 minus 0.12a. So then I'm left with 0.022 minus 0.0156, get the constants together, equals negative 0.12a plus 0.2a. So then now we have 0.0064 equals 0.08a. So a is equal to 0.08. Woohoo! So what's the answer? Well, I'll write it In meters, it's 0.08 meters. That's the natural length of the spring, or 8 centimeters, since that's how they originally gave me the information. All right, fabulous. Okay, example 7. A spherical tank of radius 3 meters has a spout on the very top that is 1 meter tall. The tank is full of water. Find the work required to pump the water out of the spout. Okay, so let's draw a picture to represent what's going on. I've got this spherical tank, and the radius of this tank is 3 meters. And then there's a little spout at the top that's 1 meter tall. And this tank is full of water. So we have to figure out how much work is required to pump this water out. Now we know it's going to be a variable force, because if you think about it, it's going to take more work to get water that's at the very bottom of the tank out than water that's already close to being at the spout. So we're going to orient everything in the y direction since we're pumping it out vertically. So I'll call this middle line right here y equals 0. Then down here, that's y equals -3. And all the way up at the top where the spout is would be at y equals 4. Okay? And the idea is we're going to slice up or imagine different slices of water in the tank and figure out how much work is required to get that water out, and then integrate or sum it all up so we can see how much work is required to pump all the water out of the tank. Okay, so here's one slice, and the volume of a slice of water in the tank is equal to pi r squared delta y. Now, here's delta y, that's the thickness, basically, of that water, of the slice of water. Now, the radius of each slice is going to change, right? You could imagine, like, the radius of that slice is going to be different than the radius of this slice. So how would I express that? I need it in terms of y, right? So let's just look at a slice flat. Okay, so the radius of that slice is going to correspond with the x coordinate of that circle. And we know from here to here is 3, right? Since it's in the tank. So we have that x squared plus y squared is equal to 9. So x, which equals the square root of 9 minus y squared, that's going to be the radius of the slice. So as you take slices at different heights y, x is equal, or the radius is equal to rad 9 minus y squared. Okay, we also need to use the fact that the weight density of water is 1,000 kilograms per meter cubed. Okay, so I have the volume of a slice of water, that would be in meters cubed. Its mass now would be 1,000 pi r squared, so that would be 9 minus y squared, dy kilograms. And I know force is equal to mass times acceleration, and I'm going to use acceleration equals 9.8 meters per second squared, because the acceleration here is just the force that's required to overcome gravitational force. So putting this all together, then my force function is equal to 9,800 pi times 9 minus y squared dy newtons. Okay? Now, when I set up these integrals, I have to also take into consideration the fact that each slice moves or is required to move a different distance, right? So whatever water is already at the top doesn't have to move as far. So imagine you have water that is up here, like at y equals 3. Say the height is y equals 3. Well, how many feet, or how many meters, excuse me, would it have to move to get out? Just 1. Versus water that's all the way at the bottom of the tank, that would need to move a total of 7 meters to be pumped out of the tank. So each slice must move 4 minus y meters. Okay, so we're going to include that in our integral. So we have here, this is a meter, the work is going to equal 9,800 pi. Let's just take that out of the integral. And then the limits have to match only what I'm actually applying work on. So I'm going to go from -3 to 3. There is no water sitting in the spout that needs to be pumped out. So don't put limits of integration or act as if you have to apply work where there is no work to be done. So we have 9,800 pi times -3 to 3. My force function has 9 minus y squared. Then I have to include the distance, 4 minus y dy. Okay, and then keep that 9,800 pi out there. It just makes things a lot easier. Multiplying everything out, and then you can integrate. It's pretty straightforward. So you end up with 1,441,200 pi joules. Or sometimes you'll see that they multiply the answer by pi, in which case you'd get 4. I'll write it first all the way out and then I'll switch to scientific. 4,433,416 joules if I multiply by pi, which is approximately 4.43 times 10 to the 6th joules. Okay, so just check with your instructor how they want the final answer, and that concludes this video.